Hi. Last time we started a new topic, which is properties of liquids, and we discussed the first property, which was the property of liquid surface. If the liquid is any liquid, not necessarily water, is in static equilibrium, then the surface of this liquid must be perpendicular to the local vector of acceleration of free fall. This is the reason why planets are spherical. Our planet Earth looks like a sphere of some radius r, which is known to be about 6,400 kilometers. Why is it spherical? Why the planet does not have such a form, an arbitrary form? Why the planet is spherical? Because inside the planet is liquid. There is a hard core at the center of the planet, but all the other volume is liquid. It's liquid because the temperature is very high and the stones melt under such high temperature and high pressure. So this is liquid, which sometimes this liquid goes out in the form of magma in the eruption of a volcano. So magma is a liquid stone, liquid stones, liquid earth, which sometimes is erupted on the surface. So the planet is liquid, but only a very thin crust on the surface of the planet is solid. That is where we live, on this crust. And the planet itself is liquid. And therefore, the local acceleration, the vector of acceleration of free fall in every point of the planet's surface is perpendicular to the surface of this liquid. And so the planet is spherical. But actually, due to planet's rotation, if we recall that a planet is rotating about the axis, so due to planet's rotation, there are some centrifugal forces in this non-inertial reference frame, non-inertial reference system, and these centripetal forces deflect the direction of vector of free fall acceleration, so that the vector free fall acceleration is not actually directed to the center of the planet. It is directed to the center on the pole, on the south pole, on the north pole, if this is a north pole, and on the equator, on the points of the equator. The vector of free fall acceleration will be directed towards the center of the planet. But in all other points, the free fall acceleration vector will be directed slightly sideways, missing the center because of rotation. And due to this effect, the planet's shape differs from spherical shape slightly. The planet is flattened at the poles and it's bulging at the equator, so that the forces of centrifugal forces tend to bulge the mass of the planet out of the center in the equator, and therefore the planet is flattened at the poles. But this effect is very small. This flattening at the poles is about 10 kilometers, and also this bulging at the equator is also about 10 kilometers. 10 kilometers is much, much smaller than the radius of the planet. Therefore, this effect is small, and the planet anyway looks like spherical, but it's slightly unspherical. And the actual shape of the planet rather looks like an ellipsoid of revolution, because it's rotating, or ellipsoid of rotation. Sometimes people say ellipsoid of revolution, sometimes ellipsoid of rotation. So that the actual shape of the planet is almost exactly the ellipsoid of rotation. But there are some deviations from this form also, because the mass of the planet is distributed unevenly. It's not a uniformly distributed mass. Somewhere there are hard stones and hard metals, and somewhere the density of the substance is smaller, and therefore somewhere the gravitational force is a little bit larger, just by a portion of percent larger, and somewhere the gravitation is a little bit smaller, and therefore there are deviations from this form of ellipsoid of revolution. So the planet is spherical as the first approximation, but this is not exactly a sphere. More strictly speaking, the planet is an ellipsoid of revolution, but this is not exactly so, because somewhere there are deviations from ellipsoid of revolution, because the density of the planet is distributed unevenly through its volume. But anyway, whatever gravitational field variations, if we know the direction of local acceleration of free fall, then the surface of the water, like surface of water in the lake or in a sea, in the ocean, the surface of the liquid, any liquid, will be perpendicular to the local direction of acceleration of free fall. That is the first property of a liquid. That is, this angle is the right angle. Another property of liquid is that a liquid creates some pressure. If we consider a vessel filled with liquid, then this liquid will have some mass and it will have some volume here. And so the total weight of this liquid, the total weight, will somehow act on the bottom of this vessel. So this force of weight will act on the bottom, and this is mg. And m, the mass of the liquid, can be expressed as the density of the liquid times its volume and acceleration of free fall. And volume may be represented as the area of the bottom, that is that area S, and the height of the liquid, the height of this liquid column. So volume will be equal to S times H, and we obtain from this formula S times Hg. Now, recalling that the pressure by definition is a force acting from the liquid divided by the area of the surface on which this force is applied, we can easily obtain from here, by dividing this force by S, we obtain that this pressure will be rho gh. So there is some pressure inside the liquid, and the pressure created by the liquid is proportional to the density of the liquid, that is, how many kilograms are in 1 cubic meter, and the acceleration of free fall, and the depth under the surface of the liquid. I have chosen to consider the depth as the distance from the surface to the bottom of this vessel, but also we can consider any depth h at this point inside the liquid, at any point inside the liquid, if it is not on the surface of the liquid, if it is somewhere on some depth, then there will be a pressure, a liquid pressure, which will be defined by this formula. Certainly this formula will be correct only if the liquid is in static equilibrium, if there are no motion, no movement of liquid inside. If there are some flows of liquid and some motion, then certainly the actual pressure will differ from this formula. But anyway, this formula will give you a good first approximation, to the pressure inside. Another property of liquid is that the pressure inside is not a vector. It's a scalar property, and actually the pressure inside is directed in all directions. In whatever direction you measure the pressure, that you will obtain the same value if you measure the pressure at the same point. At any direction in the same point, the pressure is the same. Well, how can we establish this property experimentally? We can take a vessel with liquid, and we can make a small hole here, or a small window. And if we cover this window by a rubber membrane and then pour a liquid inside, then this rubber membrane will bulge out under the pressure which is inside the liquid. The rubber membrane, which originally was flat, will become bulging outward because of the pressure inside liquid. That observation may serve as an experimental proof that a pressure in liquid is directed anywhere, in any direction. Whatever direction you choose, you will find the pressure in this direction. You can choose a vessel of a different shape. For example, you can take a vessel of such a shape, well, like this one, and you can make windows here and window here, and you can put a rubber membrane here and rubber membrane here at an arbitrary angle. And always after filling the vessel with liquid, you will observe that the rubber membrane is bulging out, creating such a concave surface or convex surface, depending on where you look at it, wherefrom you look at it. So each membrane will bulge outside, indicating that there is pressure in this direction. And whatever direction you choose, whatever direction, there is a pressure in this direction. So pressure inside liquid is directed everywhere, in any direction. This can also be understood theoretically. If I choose a small piece of liquid, a small volume, very small volume of very small mass, so that the weight of this mass, the weight is negligible in comparison with forces of pressure. So in this case, if I choose any direction and I find that pressure is acting on this chosen volume of liquid in one direction, then based on the fact that this small volume of liquid is at rest, it doesn't move because all the liquid is in static equilibrium, we can conclude that there must be equal and oppositely directed force of pressure. So the pressure acting on this small volume of liquid must be directed both in this direction and in opposite direction, so that these two forces of pressure will balance each other inside the liquid. So that this small, and whatever direction you choose, this will be correct. The forces acting along any direction will balance each other. It means that forces of friction directed here and in opposite direction are equal to each other, because this small volume of liquid is at rest. It doesn't move. Why is it at rest? Because we consider only such cases when the liquid is in static equilibrium, when there are no flows and no motion inside the liquid. That's the third property of the liquid, which means that, which can be formulated as in this way, that pressure is conveyed in all the directions inside the liquid. Another property, a property of liquid number 4, will be an Archimedes force. Archimedes force. Let's take a liquid in a vessel, and let's put an arbitrary body, an arbitrary object inside the liquid. On the surface of this object, the pressure from the liquid will act on each small area of the surface of this object. The pressure from the liquid will act from everywhere on the surface. But these points at the upper side of the body are located at the depth h1, and the points closer to the lower side of the object will be located at a depth h2, which is larger than h1, because this object has some volume, has some dimension. Obviously, this section is larger than this one. h2 is larger than h1. Therefore, the pressure inside liquid at this depth is larger than pressure inside the same liquid at the upper side of the object. And therefore, if we add all these forces of pressure acting on the object, there will be some resulting force or some net force acting upward. This net force is called a force of buoyancy, or the Archimedes force. It's obvious that there must be some force acting on an object, because pressure at the lower part of the object, liquid pressure of liquid, is larger than the pressure from the liquid acting on the upper side of this object. Therefore, if the pressure from below is larger, there must be a net force acting on the object, which is called Archimedes force. How can we calculate the Archimedes force? Let's imagine the same vessel with the same liquid inside and no object at all, no rigid body immersed in the liquid. But we can imagine the shape of this liquid, a shape of this object inside the liquid. We can choose an imaginary volume which is filled by the liquid, but it has the same shape and the same volume as the object which we considered before. But now here is a liquid, and the liquid in static equilibrium. The liquid does not move. Therefore, all the pressures from the liquid on this imaginary volume will be the same as before, because the shape of the volume under consideration is the same as before. So all the forces of pressure will be the same. And therefore, the force acting on this imaginary volume of liquid will be the same. It will be the same force, Archimedes force. But this volume of liquid is at rest. It means that the Archimedes force is balanced by the weight of the liquid, and the weight of the liquid is its mass times g, and mass is the density of the liquid times volume, this imaginary volume of the body of the object which we considered before. So the volume is not the volume of the whole liquid in this vessel, but the volume of the object under consideration. That is the volume of the displaced liquid. We say the volume of the displaced liquid. If we immerse the object here in the liquid, it will displace some amount of liquid in the volume which is occupied by this body. So mass is density, liquid density, times the object volume times acceleration of free fall. And that will be the force, Archimedes force. That will be the Archimedes force acting on the chosen volume inside the liquid. But if now we immerse our object on the same place where we considered before, then the same forces of pressure will act on our object, and the same force of Archimedes force will act on the object. So the Archimedes force in general case is the density of liquid, the acceleration of free fall, times the volume of an object which is immersed in the liquid. So such simple considerations, such arguments can be presented to derive the expression for the Archimedes force. Also, this Archimedes force is called a force of buoyancy because this force tends to lift the object upward. And there may be several different situations. For example, this object which we immersed in liquid is very heavy, and its weight, the weight of this stone, will be larger than the Archimedes force. In this case, if the force directed downward, that is, the weight of an object, is larger than the force of buoyancy, which tends to lift the object upward, then the object will move downward under the action of these two forces. If the force downward is larger than the Archimedes force, then this object will sink to the bottom of the vessel. It will go down. On the other hand, if Archimedes force is larger than the weight of the object, this may be the case when the object is very light, well, like a piece of wood, such that the density of this object is smaller than the density of liquid. Then the Archimedes force will be larger than the weight of the object, and then it means that the net force acting on this object in the liquid will be directed upward, and the object will float upward, and it will float on the surface in this case. But if these forces are the same, if these forces are equal, if Archimedes force is equal to the weight of the body, then the body inside the liquid will be in a static equilibrium, in different position. It will not go up and it will not go down. It will just float inside. It will just float inside the liquid. So the Archimedes force is an important thing. It depends on the density of water and the acceleration of free fall and the volume of the object which we immerse in the liquid. So under V we understand the volume, this volume of this object. While talking about this buoyancy force, we must certainly consider a case when the object immersed in the liquid is non-uniform, has non-uniform distribution of mass. If it has non-uniform distribution of mass, I will draw such an arbitrary object which is very heavy on this side, like there is a piece of metal, and very light on this side, so that the point which is the center of mass is here, and the weight of the object is applied to the center of mass. And such will be the case when the density or the mass is distributed unevenly. Practically all the mass is here, and this end of the object is very light. This end may be made, can be made out of wood, and this can be made out of iron, for example. Then, if such object is immersed into liquid, then the Archimedes force will be applied to which point? To the center of gravity of the water displaced by an object. So it's something like a geometrical center. That will be the point of application of Archimedes force, and that will be the point of application of the weight of the body. In this case, these two pair of forces will tend to rotate the body. It will rotate in this way, in such a way that the heavy part of the body will go down and the light part of the body will go up. So such rotation often is observed when you immerse anything in the liquid, and if this object immersed has non-uniform distribution of mass, then most probably it will turn in some way, and it will be impossible to keep the heavy side up and the light side down. It will be impossible. Such position will be not steady. Finally, the body will turn in such a way that the heavy part will be looking down and the light part will be looking upward. So that was property number 4, Archimedes force. Now we consider property number 5, which will be surface tension. Any liquid has this property which is called a surface tension or surface energy. If we consider a surface of a liquid, and if we think about molecules of liquid, then we notice one interesting thing. Any molecule inside the liquid will interact with the adjacent molecules so that the forces of interaction will be directed everywhere. Everywhere there is some molecule beside, and the interaction is with the adjacent molecules, so that the total force acting on this molecule is, on average, is 0. The total force, the net force, is 0. It may fluctuate, certainly, due to thermal fluctuations, due to thermal motion of particles, of molecules. But on average, after averaging during some short period of time, this force, this net force acting on any molecule inside the liquid is 0. Because similar molecules, identical molecules are beside this molecule under consideration, and the interaction is the same with all the identical molecules, so that the total force is 0. The situation will be different if we consider a molecule close to the surface of the liquid. In this case, this molecule will be interacting with adjacent molecules, but the other molecules in the liquid are from one side of the surface, and there are no molecules outside of the surface. Therefore, there will be some net force acting on this molecule, which is on the surface of the liquid. There will be some net force directed towards the liquid. And it means that if I take this molecule and if I try to take it away, I will have to perform some work. I will have to do some work against this force. It will not be very easy to take a molecule and take it out of the liquid, because it will be pulled backward by this force of interaction with other molecules, and therefore I will have to perform some work. It means that each molecule on the surface has some energy, has some potential energy, and in order to take this molecule out, I have to perform some work. It means that there is some potential energy on the surface, and the surface itself is in possession of some energy, which is called a surface energy. And this surface energy is directly proportional to the area of the surface, and the coefficient of proportionality is called surface energy. A surface it's called surface energy, or it's also called a surface tension. This is a surface tension. The surface tension is the energy. Oh, sorry. I wanted to place here an area of the surface. Certainly, this is S, the area of the surface, because the energy, the surface energy, is proportional to the area. Whatever area I take, whatever area of the surface I take, the larger the area, the larger the surface, the larger will be the energy of this surface. And the surface tension is the energy of a unit area of the surface. If S equals 1, if it's unity, then the energy will be equal to sigma, which is surface tension, and that will be the energy of a unit area of the surface. So either this is a surface energy or surface tension. Both terms can be used. The existence of this surface energy results in many interesting phenomena. For example, if you take a droplet of liquid in a state of weightlessness somewhere on the International Space Station, you take a droplet of liquid, it will always be of spherical form because the surface tension will tend to minimize this area of the surface, and the minimum area of the surface, surface area of a given volume of liquid will be achieved when the liquid has the spherical form. So if we take any amount of liquid, if you try to make a liquid ball on the International Space Station, then this piece of liquid will, after some vibrations, after some uncertainty in its shape, it will finally take the shape of a sphere, finally take the spherical shape because of the forces of surface tension. Because the area of the surface tends to be minimal, so that the surface energy is minimal. Any object wants to have a minimal potential energy. It tends to have minimal potential energy if it's allowed to. If it's allowed to take a minimal potential energy, then it will take the minimum possible potential energy. And the minimum possible potential energy means the minimum surface area. And the minimum surface area of a given volume of liquid is achieved when the shape of this piece of liquid is spherical. Any other shape will give you the same volume, but a larger surface area. Any other shape which differs from spherical shape. Another thing related to this same, another effect related to surface tension is as follows. We take a wire, a U-shaped wire. We take a U-shaped wire and another piece of wire which is called a jumper. This piece of wire can freely slide along the U-shaped wire, along these ends of wire. This jumper, it's called a jumper, it can easily slide in both directions, either to the right or to the left. And if we immerse such a simple device into water, we immerse it into water, but we take not pure water, we take a soap solution of water, a soap solution. Then when we take out this wire, we will find here a thin film of soapy liquid. A soapy water will form a thin film here. If we allow such a device to do what it wants to do, then we will observe that the jumper slides to the left, thus diminishing the area of this thin film of soapy liquid. The area of this film wants to become smaller, because the smaller the area, the smaller will be the potential energy of the surface. And so this will tend to move, due to this phenomenon, the jumper will tend to move to the left. And in order not to allow it to move to the left, we must apply some force to keep it in place. And if we shift this jumper a little bit to a new position by some distance delta x, we shift this jumper by some small distance delta s by applying a force F, that will cause the surface area of this thin film to be enlarged by this amount by delta S, which will be equal to the length of this jumper, L delta X. That will be the increase of the surface of this thin film. But actually, the increase of the surface will be twofold, because there are two surfaces of this thin film, like there are two surfaces of a sheet of paper. If you took a sheet of paper, you have one surface from one side and another surface from another side. The same is true here. If you take a thin film of soapy water, then there will be two sides in it, and therefore the increase in the area will be the double quantity of L delta X. L delta X is this area. So this will be the area by which we increase. This will be the value, this will be the quantity of the increase in area of this thin film. So we will perform some work. We will perform some work, which is by definition the force applied to the jumper times the displacement of the jumper. The force times the displacement x. That work will be performed by an external force, and that work will go to increase the potential energy of the surface of the thin film. And the increase in potential energy, I will denote it by delta E. The increase in potential energy can easily be calculated from this formula. It will be the constant quantity, the surface energy, the energy of a unit area of the surface, multiplied by the change in delta S, that is, the change in delta S. And that will be finally sigma times 2L delta X. Now, if we compare these two expressions, force times delta X here, and the final expression, which also contains delta X, then we will easily conclude that delta X may be cancelled, and the sigma, the surface tension here, the surface tension will be force applied, this force divided by 2L. That will be the relationship between the force applied here to the jumper and the surface tension. If we look at this quantity, at this physical quantity sigma, we can easily conclude that the units of measurement of sigma, the units of measurement will be what? Energy is measured in joules, and surface area is measured in meters squared. That is from this formula. And from this formula, the same quantity will be measured in Newton. F is measured in newtons, and length is measured by meters. So the same quantity sigma will have one unit of measurement here, and as if different unit of measurement here. We will continue this discussion after a short interval. Okay, after this short interval, we continue discussing different properties of liquids, and we came to conclusion that in one case this surface tension is measured in joules over meter squared, and in a different case, in another case, the same physical quantity is measured in newtons per meter. Actually, this is the same unit of measurement. It's easy to see that if we multiply this formula by meter, both numerator and denominator will be multiplied by meter. Then we will obtain here Newton times meter, and in denominator we will obtain meter squared. And Newton times meter is force times displacement. Force times displacement is what? Force times displacement by definition is work. Work is measured in joules. So this is joules over meter squared, the same as here. Therefore, these two different presentations of the unit of measurement of the surface tension is actually the same. Is actually the same unit. Well, I would like to consider a small problem related to surface tension or surface energy, so that you could feel what does it mean, the surface energy. I will consider the following problem. First of all, I will give you a measured quantity of sigma for water. If we take water, pure water, then in the international system, this surface energy of water has this amount, joules per meter squared. It seems to be very small, just like 0.07 joules per meter squared. Meter squared is a large area, and so on each meter squared contains such a small amount of joules of surface energy. But if we consider some particular physical process, then we will discover that sometimes this small quantity plays very significant role. Consider 1 liter of water. So this is 1 liter of water, 1 liter, so that this is a cube of water with the side of 10 centimeters. This is 10 centimeters. So that is 1 liter. Volume of water is 1 liter. And we take this volume of water and spray this volume into small droplets, such small that the dimension of droplet, the diameter of a droplet, is about 1 micron. 1 micron is 1/1,000,000th part of a meter. So we spray this amount of water into small droplets to obtain such a mist. And the water droplet's diameter is approximately 1 micron. 1 micrometer. This quantity is called micrometer or micron, two possible words. So the question is, what amount of work should be performed in order to turn this 1 liter of water into small droplets, in order to spray small droplets in them of such dimension we want to convert 1 liter of water into a mist of small droplets of water. What amount of work should be performed in order to spray this amount of water? So the work performed will be the change of surface energy in water. It's obvious that 1 liter of water will have some surface and will have some surface energy, but if we spray this amount of water into small droplets, then the surface of all the small droplets will be much larger, and so we will have to increase the surface of water, and therefore we will increase the surface energy. The surface energy will be different, and it will be increased. So we will calculate the surface energy of the final state, which is the total surface of total area of the surface of all droplets. I don't know how many droplets are there. Let there be n droplets. So this is the surface area of all the small droplets. I don't know how many. 1 million, 1 billion, I don't know. We will calculate the number of droplets, but n is a large number. It's a number of droplets. That is the final surface area. So that is the final surface energy. And we will subtract from the final surface energy the initial surface energy of 1 liter of water. That is the initial, when we had just 1 liter, one piece of water, one single amount of water. That will be S1. So in order to calculate it, we will certainly have to calculate the difference between these two surface areas, the area of the surface of n small droplets minus the area of one single volume of water. First of all, it's not difficult to assess by the order of magnitude this quantity S1. S1 by the order of magnitude will be what? If initial water was contained in a cubical vessel, then the total area of the surface of this cube can easily be calculated. It's 10 centimeters times 10 centimeters. That will be the area of one face of the cube, and there are 6 faces of such cube. So 6 equal faces times 10 centimeter squared, which is the area of one face of the cube. So that will give us in centimeters. 10 squared is 100 times 6. That will be 600 square centimeters. That is the initial volume, initial surface area of this piece of water, of this amount of water. So now we have to calculate the final surface area of n droplets. That will be the number of droplets times the surface area of each droplet. So what will be the surface area of each droplet? If we know that the dimension, that the diameter of the droplet is about 1 micron, certainly different droplets will have different diameter, will have different dimension. Not all the droplets will be equal in dimension. They are different, but by the order of magnitude, they are 1 micron. So I have to calculate by the order of magnitude. I have to make approximate calculation. And approximately, if we know the diameter of each droplet, then the surface area will be approximately by the order of magnitude equal to d squared, which is very rough estimate. Certainly, I can use this formula like PD squared, but as the surface of the surface area of a single droplet. But this coefficient is senseless because I don't know the exact dimension of each droplet, because it's given just like by the order of magnitude. So I have to assess, I have to make an assessment, I have to carry out an approximate calculation. So the surface area of one droplet is d, and the number of droplets can be assessed as the initial volume divided by the volume of each droplet. Initial volume is 1 liter. That is initial volume, which is given as 1 liter. And the volume of one droplet, again, by the order of magnitude, it will be d cube. That is the initial volume of liquid divided by the volume of each droplet. In this way, we obtain the number of droplets. And I have to multiply by the surface area of each droplet on average. So this will be approximately initial volume divided by d. Initial volume is the volume of this cube is 10 centimeter cube. 10 centimeter cube, that is the initial volume, and d is 10 to the minus 6. But if I want to calculate in centimeters, then I have to convert meters into centimeter. So 1 meter is 100 centimeters. So 1 meter is 100 centimeters. And that will give me, that will allow me to make calculations in centimeters rather than meters. But anyway, it's possible to carry out calculations in meters. Then I will have to convert centimeters here in the denominator into meters. It's the same, no, not much difference. So 10 to the minus 6 times 100 will be 10 to the minus 4. And then it means that 10 to the power of 4 will be in the denominator. 10 to the power of 4 will go here. And here will be 10 cube. And a centimeter cube divided by centimeter will be centimeter squared. So that will be 10 to the power of 3 times 10 to the power of 4 will be 10 to the power of 7 centimeters squared. So that is 10 million square centimeters, 10 million. The final area of all the surfaces of all the n droplets is about 10 million centimeters squared. And the initial area was just 600 centimeters squared, which is 600 is much, much smaller than the final area. So I can neglect this quantity here. It's practically zero in comparison with the first term. In comparison. So approximately that will be sigma Sn, because the second term is very small in comparison with the first term. 600 is much, much smaller than 10 million, certainly. And therefore, the total energy may be calculated as the surface tension, which is given by this quantity. I will finish my calculations here, times the Sn, which is 10 to the 7th power. So I will have to take 10 to the 7th power, which is the S final area of all the droplets. But this is given to me in centimeters squared. And I have to take it into account because the sigma is given in joules over meter squared. I will have to figure out what it will give me, centimeter squared divided by 1 meter squared, in order to obtain the correct answer, times what is given here, 0.0725 joules by meter squared. Well, what is 1 meter squared? What is 1 meter? It's 100 centimeters. So 1 meter squared is 10,000 centimeters. That is 100 squared. 10,000 centimeters. So instead of 1 meter squared, I have to use 10 to the power of 4 centimeters squared. And then I will have centimeter squared in the denominator of this formula and centimeter squared in the numerator. And centimeter squared will be cancelled, and the only quantity remaining here will be joules, just what I need, because I'm calculating the work. I'm calculating the amount of work to be performed, and work is measured in joules. And so that will give me what? 10 to the power of 4 here, multiplied 10 to the power of 7 divided by 10 to the power of 4. That will give me 10 to the power of 3. 7 minus 4 is 3. And multiplied by this figure, multiplied by 0.0725, and I know that it will be joules, in joules, and that will give me 3. I have to shift the decimal point by 3 digits. That will give me 72 0.5 joules. Approximately, certainly, all the calculations were carried out approximately. And if so, if the calculations were just by the order of magnitude, then I don't have to present such a definite answer, such a strict figure up to one figure after the decimal point. As the calculations were carried out to the order of magnitude, then all this should be written as about what? About 100 joules. We approximate the given number by 100, approximately, by the order of magnitude. We have to spend about 100 joules to spray 1 liter of water into small droplets of 1 micron diameter each, approximately. So what does it mean when I say approximately 100? It means that it may be approximately 90 or 70 or 80 or maybe 110, 125. By the order of magnitude, all these figures are the same. And as my calculations were carried out by the order of magnitude, then in this approximation, the answer may be given like 100 joules. So in order to spray 1 liter of water into small droplets, I have to perform work of about 100 joules. This is not a small work. This is not a small figure. It's a considerable amount of work. So next topic I want to consider, if we discuss the surface tension, then I would like to discuss the pressure inside the liquid. Okay, the pressure inside, I will continue here. Let's consider a small droplet of water or any other liquid. A small droplet. We have just discussed droplets of 1 micron diameter. So this is a small droplet which may be 1 micron in diameter, maybe less than 1 micron. A small droplet of water. There is a surface tension here on the surface of this water droplet. There is a surface tension, which is the surface energy, which means that if I want to take a molecule out of here and pull it away from this liquid, I have to perform some work. And which means that if a molecule of water appears to be here, close to the surface, then it will be pulled inside the droplet, and it will stick to the droplet and become part of it, because there is a force acting on each molecule and directed inside the droplet of this water. So it means that if I somehow change the, if I happen to change the volume of this, if I happen to change the volume of this droplet, if I happen to change the diameter by a very small quantity, so the radius of this droplet will be r, and I imagine that I change the radius by a very small quantity, delta r. If I change the dimension by a very small quantity, delta r, then I will have to perform some work because the surface area will be changed. The surface area will be changed, and I will have to perform some work. So if there is some pressure inside this droplet, then the force acting on a unit area will be just pressure, because pressure is the force acting on a unit area, and I will have to perform work in order to increase the radius of this droplet by a very small amount. I don't pretend that I can inflate this droplet to a larger droplet, just like as if it was a gas. No, I just imagine that I change the radius by a very small amount, and so that there is a pressure inside the droplet and pressure outside the droplet. And let's pressure outside be P1 and pressure inside be P2. And if I change the radius of this droplet, then the difference of this pressure will somehow resist the changes of radius. And if I change the radius, I will have to perform some work. The work will be difference in pressures by difference in pressures by change of volume of this droplet. So this droplet will have some volume. And that will be difference in pressures, and the change in volume will be the volume of this very small layer by which I change the dimension of the droplet. And the volume of this very small layer will be the surface area S, times the thickness of this volume, thickness of this layer, delta R. That will be the change in volume. That will be change in volume of the droplet. And that work will actually go to increase the surface energy. And the surface energy is characterized by surface tension. And so this change in volume will be, this work performed will, the work is performed in order to change the surface area, change the volume and surface area. And so this work will go into changing the surface energy. And that will be sigma delta S. And the surface S, the surface of this droplet S, is known to be 4 pi r squared. So delta S will be 4 pi final radius r plus delta r squared minus initial radius r squared. And that will be 4 pi r squared and r squared will cancel here, and what will remain is 2 r delta r plus delta r squared. Delta r is very small variation in radius, so delta r is much, much smaller than r. Therefore, this term may be neglected here. It will be 0, and the only term remaining will be 4 pi times 2, that will be 8 pi times r and times delta r. That will be the change in surface area. And the change in surface area must be used in this formula, and that will give me sigma times 8 pi r delta r. And now combining these two formulas, these two expressions, this one and this one, I can write that the difference in pressures P2 minus P1 will be equal to 8 pi r delta r. Delta r will be divided by delta r, so small variation in radius will cancel. Delta r will cancel in this formula, and so small variation in pressure will be equal to 8 pi r divided by s, and s is known to be 4 pi r squared. So 8 pi r divided by 4 pi r squared will give us 8 pi divided by 4 pi, that is 2, r divided by r squared, that is r, and what remains missing, that is sigma, which must be here. That is, sigma is here, but I have forgotten to put it in this formula. Certainly sigma is here. That was missing. That was missing from this formula. It was here, sigma is here, together with 8 pi, and so sigma should be always together with 8 pi sigma. So we have derived a very interesting formula that the pressure difference inside the small droplet of water and outside the small droplet of water, due to the surface energy on the surface of this droplet, will be defined by this formula. The pressure difference is directly proportional to the surface energy and inversely proportional to the radius of the droplet. If we take very small droplet with very small radius, then the small quantity will be here, the small value in denominator will give you large quantity, large value for pressure difference. Let's make an assessment. What will be the pressure difference inside the small droplet of water like this one, which we have already considered, like having a diameter of 1 micron or even smaller? I will take a smaller droplet. Let's consider a very small droplet of diameter about 10 nanometers, which is 10 to the minus 8 meters. What is 1 nanometer? It's 10 angstroms. 1 nanometer actually contains just a few molecules, just about 3 or 4. So such a diameter of 10 nanometers will contain just some dozens of molecules, about 20 to 30 to 40 molecules on the diameter. So this is a very small droplet of molecule, very small droplet of water containing just about 40 molecules on its diameter, on the order of magnitude. I consider very small droplet, very small. So if there are 40 or 30 molecules on the diameter, how many molecules in this droplet? We must take the diameter cube, and the number of molecules on the diameter will be in cube. So if you take 30 in cube, it will be about 30,000 molecules. Well, it's a very small droplet, but anyway, it will contain about 30,000 molecules of water. About 30,000 molecules of water. So 30,000 is anyway macroscopic object. It's macroscopic. And it means that all the macroscopic considerations, not quantum mechanical, but macroscopic, classical, which I have used so far, will apply, most probably will apply to even to such small droplets of water. It's small in dimension, just 10 nanometers, but it still contains about 30,000. What is about? I told you by the order of magnitude. It means that I consider such droplets which contain maybe 20 or 25,000 molecules, or 35 or 40, maybe 50,000 molecules. Anyway, very small droplet of water, but containing still very large number of molecules. Very small droplet containing very large number of molecules. Therefore, even such a small droplet may be considered classically. And applying our formula for pressure difference inside and outside. By the way, what is the pressure outside in the atmosphere? It's atmospheric pressure. It's atmospheric pressure, 1 atmosphere. So what is the pressure inside as compared to 1 atmosphere outside? It will be given by this formula 2 sigma over r. And we know sigma for water, it's 0.0725. In the international system, that is joules per meter squared. And we have to multiply by 2 and divide by r. And r is 10 to the minus 8 meter. Divided by r is 10 to the minus 8 meter. Well, what is 725 multiplied by 2? That will give us like something like 0.145. Something like that. Divided by 10 to the minus 8. Everything in international system of units. That will be 10 to the power of 8 multiplied by 0.1, approximately by the order of magnitude. 10 to the power of 8 multiplied by 0.1 will be 10 to the power of 7. And what is it? Joules over meter cube. Joules over meter cube. So, in order to compare this with the atmospheric pressure is about 1 kilogram force on 1 centimeter squared. So how many centimeters squared? If I multiply this expression by 1 meter, both nominator and in, if I, well, something's wrong here. This is I have misused the units of measurement somewhere. So this is the sigma is certainly measured in joules. In joules, it's better to say Newton per meter. 1 joule is Newton by meter per meter squared. That's correct. But that is the same as Newton over 1 meter. So that is the same as Newton divided by 1 meter. And so in the end, we will obtain Newton over meter squared. Yes, that's correct. Newton over meter squared. So how many newtons over meter squared in 1 atmosphere? I want to compare this pressure inside the droplet with the pressure of 1 atmosphere. How many newtons per meter squared in 1 atmosphere? 1 atmosphere is 1 kilogram per centimeter squared. There are 10,000 centimeters squared in 1 meter squared. So 10,000 centimeters squared in 1 meter squared. Therefore, 1 atmosphere, I will put it here, 1 atmosphere is 10,000 centimeters squared in 1 meter squared times Newton, and Newton is 1 kilogram on 1 meter squared. 1 kilogram is 10 newtons, so that will be about 1 kilogram forces. I told you that 1 kilogram force is the weight of 1 kilogram mass. That is, if you take 1 kilogram times g, that will be approximately 10 newtons. So 1 kilogram force is approximately 10 newtons. So if I talk about 1 atmosphere, which is 1 kilogram force over centimeter squared, approximately, that is 1 atmosphere. Then 1 centimeter force is 10 newtons, and 1 centimeter squared is 10,000 is 10 to the minus 4,000, 4 power of 4 meters. So I obtain this amount of newtons per meter squared. That will be 10 to the 5th power of newtons per meter squared. This is 1 atmosphere. And here I obtained 10 to the 7th power Newton per meter squared. That is about 100 atmospheres. That's correct. The pressure inside such a small droplet will be about 100 atmospheres only due to the surface tension, on the surface of this small droplet of liquid. About 100 atmospheres in such a small droplet of liquid only due to the surface tension. Well, if I increase the radius of the droplet by, say, 100 times, if I increase it by 100 times, so that it will be it will be just 100 times larger, then it will be 1 micron, 10 to the minus 6 meters. It will be 1 micron. So I increase the diameter of my droplet by 100 times, then the pressure difference will be decreased by the same amount of 100 times. And then I will obtain the additional pressure inside such a droplet 100 times smaller. That will be just 1 atmosphere. So if I take a droplet of water about 1 micron in diameter, 1 micron, the pressure will be inside, additional pressure, about 1 atmosphere. But if I decrease the radius down, decrease by 100 times down to 10 nanometers, then the additional pressure inside the droplet will be about 100 atmospheres. That's the result of surface tension. That's the result of surface tension. So surface tension is a very important physical property of any liquid, not only water. Any liquid has its own surface tension. And how to measure surface tension, how to measure experimentally, it's an interesting thing. Probably I will have a few minutes to tell you how this surface tension is measured experimentally for any liquid. Suppose I have a vessel with liquid and I put here a tube of small diameter. A tube of small diameter. Then if this is a water, we will talk about it. If tube is made of glass and this is water, then by experimental observation it's known that water is wetting the glass. It means that water tends to be attracted to the glass. It means that the water surface near the glass wall will have this form of this, will have this shape, concave shape, and the water inside the small tube will go higher than the level of water outside the tube. Inside the tube it will be somewhat higher, and the diameter and the water surface will be concave if you look from above. So water will go up due to molecular forces acting between water and the glass. And so here will be the radius of this spherical surface. The radius of this spherical surface will be approximately equal to the radius of this tube. And this radius is here defining the pressure difference in the atmosphere and just in water below this curved surface. So the pressure difference, delta P, in atmosphere and in water will be given by 2 sigma divided by r. R is known because this is the diameter of our glass tube. We can easily measure r because this is the diameter, the internal diameter of glass tube. So r is known. Pressure difference can be calculated easily because pressure in the atmosphere is 1 atmosphere, and pressure here will be calculated as 1 atmosphere, the pressure outside, minus this column of water, which will perform negative pressure here. That will be the water density, acceleration of free fall, times this height of this water column. So that will be the pressure difference in our experiment. And the only thing, in order to calculate the surface energy. We have to measure the diameter of the tube and the height of this water column, H. The H will define the temperature, the pressure difference on the two sides of this curved surface. And knowing the pressure difference, delta P, and knowing the radius, we may easily calculate this quantity, which is surface tension. So in such simple experiment, we may measure the surface tension experimentally for any kind of liquid. On this point, let us finish this lecture.